Okay, good morning, everyone. I want to welcome you to another theory of statistics class. Before I get started today, I actually like giving another opportunity. So, for those of you who score less than 80 in the midterm one, I'm actually there's going to be a makeup and information about the makeup will be posted before the end of today. So I'm going to repeat myself. Um, for those of you who want to improve on your grade, you score less than 80% in the recently concluded midterm one, or you miss the test, okay, um, there's going to be another opportunity. I'm actually going to make announcements regarding that, regarding the detail on Canvas today. Make sure you keep track of the announcement section. So there's going to be a deal that I'm actually going to propose. It's not compulsory. It's just for those who want to improve on their grade. Okay, so I want to go into today's material. Of course, the focus is going to be on multivariate joint distributions. Before now, I walk you through univariate functions. From univariate functions, we talk about univariate distributions of the discrete and continuous type. I remember I also walk you through the bivariate functions and the bivariate normal distribution. But the focus today, we actually want to go beyond, considering two measurements at a time to more than two measurements. Okay, that's going to be the focus today. I attach a worksheet on Canvas. If you take a look at what I have here, I put some exercise here, and of course, the worksheet is on Canvas. My TA is actually going to walk you through stuff like this in the lab, but the solutions to this exercise here on the bivariate, of course, like I said, I've uploaded that on Canvas. Okay, so for you to be able to see the connection between the univariate and the bivariate and multivariate, I think I'm going to have a review, okay? And what I need you to do is to pay attention, okay? Now, if I have xi, particularly if I want to talk about univariate normal, okay, I can actually say xi follow normal with mu I sigma I squared, okay, where I go from 1, 2 to n, there's possibility, or let me just say to p, there is possibility that we have a separate univariate normal, situations where we believe there's no correlation among these variables. Of course, I'm actually going to have f of xi to be 1 over square root of 2 pi sigma square I, okay, exp, okay, negative half xi minus mu I, okay, divided by sigma xi, sigma si, squared. If you take a look at what I have here, you actually are going to see this centered on f of xi, which could be f of x1, or f of x2, and so on like that, okay? And of course, you know, the mu I, okay, lies in the real number, and of course, the sigma, the sigma high, okay, lies in the positive real number, because the sigma, or squared actually need to be positive. Okay. Now, this is when I want to consider one variable at a time, and the variable followed normal distribution. But if I want to consider two variables at a time, where there's a relationship between variable x1 and x2, okay, which is what we did the other time, bivariate normal, okay. I'm actually going to say x1 x2, okay, I'll follow normal distribution, okay, and they follow normal distribution. I'm actually going to have mu1, mu2, okay, and when I have mu1, mu2, I'm actually going to have this guy, okay. This guy here is actually the variance covariance, which is going to be sigma 1 squared, sigma 2 squared, okay, rho sigma 1, sigma 2, rho sigma 1, sigma 2, okay. So if you take a look at this, this guy is this guy. So my f of x1 x2 is going to be 1 over 2 pi sigma 1 or sigma 2, or into 1 minus rho squared. So ESP into negative half 1 minus that, okay, into x1 minus mu1 sigma 1 squared minus that, x1 minus mu1 divided by sigma 1, x2 minus mu2 divided by sigma 2, then x2 minus mu2 divided by sigma 2 all squared. Now, if you, I wanted to see the connection, because between this, because I'm also going to write the one for multivariate. This is for univariate situation. Univariate situation where we can actually focus on one variable at a time, because of the fact that they do not have connection, okay? But situation where I got two variables, okay, and they are, jointly, normally distributed, okay, I'm actually going to say x1, x2 follow normal. This is the mean, okay, mu1, mu2, and the variance covariance, what I defined in, and this is the joint, the density that I actually talk about. We discussed this on Wednesday. I remember we also discussed something that has to do with the conditional distribution. We talk about the conditional mean, conditional variance, and so on like that. But you know what? I want to go into situation where I'm having more than two variables. I want to have more than two variables, okay? I want to consider a situation where we got more than two variables, okay? When we have more than two variables, and they are jointly normally distributed, okay, we actually have multivariate normal, okay, multivariate normal, okay, which is the focus of today, one of the focus, the multivariate normal, okay, what I mean is I have x1, x2 until I get to xp, okay. I have so many fixtures, okay, and they are distributed normally. So I'm actually going to say x follow, okay. This particular x here is a vector, that is x1, x2 up to xp, okay. Follow normal distribution, okay, with I'm actually going to have with mu vector and the variance covariance. Okay, now when you take a look at this guy, okay, this guy is mu1, mu2 up to mu p. Okay, now if I want to write the f of s, right now I'm actually going to have 1 over this p raised to power 2. The what I'm going to have here, the determinant of that raised to power half. Then I'm actually going to have this guy, the negatives half x minus mu transpose, x minus mu transpose inverse that, then x minus mu. Please, I need you to pay attention. Okay, this is multivariate normal. If I want to write multivariate normal, it's going to be in terms of a matrix. The idea of a matrix algebra is going to be in use. Okay, I got a P here because I want to talk about P numbers of variables. Okay, this is going to be the determinant of the variance covariance matrix. Here, this is going to be the inverse of a covariance matrix. And of course, here I'm talking about x minus mu, then the transpose of that. Okay, now this is what we call multivariate normal. Now I've given you univariate normal, I've given you the bivariate normal, and I've also given you the multivariate normal. Okay, you know what I want to do right now? I actually want to walk us through our example. But before going into the example, okay, there's something I actually so like I said, pay attention. Pay attention. Did you understand? You asked me a question. Okay. The next thing that I want to do now is this. If I actually, if you take a look at what I have here, for instance, if I want to write bivariate in matrix form, okay, I have S1, S2, okay, follow normal with a mu vector, and that mu vector is mu1, mu2, then this guy, the variance covariance. Now, there's something I wanted to see. Some of you may be wondering, how am I going to get this guy here? And how am I going to get this guy here? Please pay attention. How am I going to get this guy here? How am I going to get this guy here? Okay, now, this guy is actually this for 2 variable is this. Okay, for 2 variables is that. In the diagonal variances, of diagonal covariance, the covariance is the product of the correlation and the respective standard deviation. Okay, now if I want to get the determinant here, okay, the determinant, I want to get the determinant of that. The determinant of that in the matrix is going to be this multiplied by that, okay, this multiplied by that, minus this multiplied by that. That multiplied by that will be this. Please pay attention. If you don't understand, look at what I've just did. This times this. The determinant, this guy here means the determinant of this is what I'm trying to talk about. That is a notation, not the absolute value. Okay? In maths, we also use this notation as absolute value, but right now in matrix, it is determinant. And how do we find determinant? So this multiplied by this minus that multiplied by that. So if I factorize this guy out, what is common, actually going to have this guy, right? When I factorize it out, so this guy is the same thing as this. If I know the variances and I know the correlation, I'm actually going to be okay here. Now, how do I find, the moment I was able to find this, I can find this guy here. This is what we call inverse. Inverse of covariance, or inverse of variance, covariance matrix. And if I want to find the inverse is going to be the adjunct, okay, adjunct divided by the determinant. Okay, now the adjunct, I need you to pay attention. The adjunct, I'm going to come here. I'm going to switch the element in the diagonal. In switching the element in the diagonal, I'm actually having this guy. Can you see that? I switch this, but I will multiply. I'm not going to switch this. I'm just going to multiply by -1. Okay, so I'm actually having sigma 1, sigma 2. Okay, sigma 1, sigma 2. Okay, now divided by what I got here, divided by the determinant, which is going to be this guy here, 1 minus that. Now, this is the inverse. What I got here is what we call the inverse of that particular matrix. Okay, I want to walk us through. Now, another thing I also want to mention is this. We can also talk about linear combination. Okay, for instance, I have linear combination involving more than 2 variables. Okay, if I define that as this, y equal to c prime x, where s is a vector. For instance, I'm having this C1, okay, I have a C1, X1, C2, X2, until I get to CP, XP. This is a linear combination. In matrix form, it is this guy. I want to find what is the expected value of a linear combination now. It's actually C prime, or let me be calling that transpose. Then I'm actually going to have the C transpose expectation of S. I'm actually going to have C transpose mu. Okay, I can also find the variance of Y. Okay, the variance of a C transpose S. Okay, the C here is just the constant. Okay, so here I'm actually going to have C transpose, variance of S, C, which is going to be C transpose. What is the variance of S? Is this guy. The variance of, the variance covariance is this guy, C. Look at that. Okay, so this is the mean. This is the variance of a linear combination. Now what I want to do now, I want to walk us through, let me do this. Okay, I want to walk us through an example, and I need you to pay attention. Measurements were taken on an attack and heart attack patients on their cholesterol level. Okay, with due respect to patient that have heart attack. Okay, actually a measurement was taken after them having heart attack. The measurement were taken on their cholesterol level, okay? But, following the heart attack, they were given medicine to reduce the cholesterol level, okay? But, and that measurement was taken in a repeated version, okay? In a repeated version, on day 0, on day 2, and on day 4. Okay, now I'm going to give you the mean. Okay, the mean for day 1, day 2, and day 4. Okay, so the example that I want to talk about. Now, the sample mean vector now, released in that regard. Okay, the sample mean vector released in that regard. I got variable. Okay, and the mean. Okay, X1 represent 0 day, X2 represent 2 day, and S3 represent 4 day. Okay, please pay attention. And the mean is 259.5, 230.8, 221.5. Okay, now, this is like the average. I'm talking about, cholesterol level. Of course, if you see what happened on N patients, okay, N patient, maybe like 20 patient or 50 patient, after 0 day, this is the average of the cholesterol level. After 2 days of following the heart attack, this is the mean cholesterol level. You can see what happened is decreasing by the day. Now, this is like the mean vector, okay? Now, the variance, they also gave us information about the variance. Please pay attention. Okay, they gave us information about the variance. Okay, so the covariance matrix was actually given as this: 0 day, 2 day, 4 day, and of course, 0 day, 2 day, 4 day. Okay, now we have this from 2276 1508 813 1508 1508 2206 1349 813 1349 1865. Please pay attention. This is the mean. Okay, on 0 day, 2 day, that is the mean. Whenever we have a mean, there will be variances. And because this is a repeated situation where you collect observation from the same person more than one time, we call that a repeated measure. Okay, then if there's a repeated measure, there's going to be relationship between what they have from me on day 0 and what they get from me on day 2, and so on like that. And that's why here, okay, these are the covariances. Here, this guy are the variances. Okay, these are the covariances. So right now, from here, I'm actually going to say my mu vector is this guy. So which is like the mean 1, mu 2, and mu 3. My variance, covariance, now please pay attention, okay? So it's what I have here. 2276 1508 813 1508 2206 1349 813 1349 865. This is the covariance matrix from there. This is the mean vector. Okay, now several questions can be asked, okay, on this. And what are the questions, okay, that we actually want to ask, that we're going to ask, that I want to ask right now? Please pay attention. Like I said, pay attention. Okay, now, if a question asks, suppose we are interested, okay, here, based on this question, suppose we are interested in the difference x1 minus x2, okay, which is the difference between the 0 day and the second day measurement. Okay, suppose what we're interested in. Go ahead.
So you just said that since this is a repeated measurement of the same patient.
Exactly.
There is going to be a correlation, or is there going to be a covariance?
Yeah, covariance. Covariance lead to correlation.
Is it correlation leading to covariate, or is it vice versa?
Okay, this is what happened. You can't get correlation without covariance. Now, look, that's a good question. Okay, let me write it here. Correlation, which is still part of what we want to do today. Correlation is covariance divided by sigma x, sigma y. Which means, without this covariance, I can't get correlation. There have to be a covariance. Covariance means they vary jointly. They have to vary jointly before relationship will exist. We're coming back to that because it's part of the topic for today. Okay, now, based on this here, if I'm interested, I know that here, how many variables do we have? We have x1, x2, x3, right? I may be interested in the difference between their cholesterol level on day 0 and day 2, or day 0, day 4, or day 2, day 4. Now, if I'm interested in this, please pay attention. Okay, if I'm interested in that, I want to look at the difference. Then this is going to be linear combination. This is a linear combination. Please pay attention. Okay, if I'm interested in this, I want to get the mean of that. I want to estimate this guy. I also want to find the mean. And if you take a look at what I did here, this is for situation where I'm putting all of that into consideration. Okay, now right now, I actually, my C, my constant in that situation, okay, is going to be 1. What is the coefficient of this? -1. I'm not interested in the third one, 0. What is the third one? The third one is day 4. The question is saying, please pay attention, okay? Pay attention. Look at the question. Suppose we are interested in the difference in x1 minus x2, which is the difference between 0 day and the second day. Okay? Don't forget, I have 3 days. Okay? I have 4 days. This is the third one, but I'm not interested in that. The one I'm not interested in will be 0 under the matrix. So here, okay, so this guy, I'm actually going to have 1, -1, and 0 for that. Okay, now, if I have 1, -1, and 0, so what I'm trying to say here, the C transpose is going to be this, based on this question, is going to be that. Now, if it is this right now, if I want to find y equal to this, don't forget, I have 1, -1, 0. Okay, my x now is x1, x2, and x3. x1, x2, and x3. Okay, it's my x. Okay, which is represent the day. Now, I said I'm going to make use of this formula here, CT mu. Now, when I say CT mu, so if I want to find expected value of y now, okay, I say CT mu. Okay, what does that mean? Okay, the CT mu will be 1, -1, 0. Then I'm actually going to make use of the means. Look at that. Mu is we're going to be a vector. I'm going to make use of those mu. Yeah, this guy. I'm going to make use of those mu. So 2, 5, that 0.5, 2, 3.8, 2, 2, 1.5. If you take a look at that, if you multiply this by this, you know what you're doing? It's more or less like you're doing this minus that. That is what it looked like. So what do I get? So here, I got 28.7. This is the mean of the difference, the average of the difference in cholesterol level between day 0 and the second day. Now, if I have that as the average, I can find the variance. I can find the variance as well. Please pay attention. What is the variance of a linear combination? Is that. So I want to find the variance of y, which is the variance of x1 minus x2. Okay? That's exactly what I want to find. And based on the formula here, it's going to be C transpose that guy C. Now, what is the C transpose here? The C transpose here is a 1, -1, 0. Then what is this? Which is what you're given here. Okay, that's what you're given here. Okay, you're given 2276 1508 813 1508 2206 1349 813 1349 1865. Okay, what is the transpose of that? Because this C transpose C, so this is going to be 1 negative 1 0. Okay, and for us to use this to multiply this, you have to remember what you did in matrix algebra. Matrix algebra. So, well, when you're done, you're actually going to have this. Okay? What do we have? We have a single result. A single value, a single value. Then this is the takeaway. I want you to listen to the takeaway. I have a single value for mean. I have a single value for the variance. Then it means if I'm working on x1, x2, x3, if I'm working on a multivariate normal, and I want to talk about linear combination, the linear combination of multiple variables is actually going to lead us back to univariate. And that's why we're having a single answer. Single, can you say single answer? Single answer. We're back at univariate. That is exactly what this guy means. Okay, now I want to go back. I want to project right now, since you have enough information. Like I said, attendance of lecture now, very, very important. What we're doing now, can assure you, very critical, okay? Very, very critical, okay? Okay, now, I want to go to some other. Now, I just review. We just did something. I reviewed bivariate. I reviewed multinomial distribution. Now, what I want to talk about, because I'm going to. I just handled multivariate normal, bivariate normal. Now, when we have discrete distribution, can we also have